Another amazing thing that relational databases do is support concurrent execution by a number of different programs and users and so forth. And we want to kind of drill into that a little bit and look at some of the abilities that the databases have, the properties that they exhibit, and some of the problems that you might encounter in this area. So let's just talk about concurrent execution for a moment. First of all, of course, a database is a shared resource, unless you're using something like SQLite inside of a Python process or something like that. You're normally going to be accessing a database that's running on a server that could, in principle, be accessed by thousands of users, essentially accessing it concurrently. It's important to kind of think in terms of what sort of concurrency are we after here. Are we thinking physical concurrency? Well, no, we can't have two separate processes or two separate users that are writing different data to the same part of the disk at exactly the same time, where the data are stored. But logically, yeah, we totally want to be able to provide the illusion that the database is accessible to everyone concurrently. And what the database provides is basically a mechanism that behaves as if each of the users that are accessing the database at a given time are the only one that are using the database, which is remarkable. And this concurrency mechanism relies on the use of transactions, which we've just talked about recently. So the things that we're going to talk about today have to do with concurrent transactions that are being executed, not so much kind of one-off statements that you're running from a tool or from the command line or something like that, but within the context of a transaction. So these are some of the more theoretical kind of underlying properties of a transaction that are implemented in the concurrency model for relational databases. So the acronym is ACID, and the four properties are atomicity, consistency, isolation, and durability. So atomicity basically means that the transaction itself completes as a unit. And that's what we talked about kind of most specifically with respect to transactions when we introduced that idea. So it's an all or nothing proposition. Either all of the database operations that are encapsulated inside of a transaction succeed, or if any of them fails, the whole thing rolls back and the database is restored to the state that it was in prior to the beginning of the transaction. So there's never a partially executed transaction. Even in the case where the database crashes, or the computer that it's running on crashes, or the network connection crashes, or the disk crashes, the database has a mechanism for recovering when it's restarted that will essentially roll back partially completed transactions. So that atomicity, really important, all or nothing. It's all going to work or none of it's going to work. Secondly, the database transaction will exhibit consistency. So when we talk about consistency, I'm speaking in fairly broad terms. So things like the notion that primary keys are properly observed. In other words, there's no duplicate primary keys in any given table. Or that foreign key relationships are correct, that when you have a foreign key that refers to another table, the table being referred to has a row with a primary key that matches a foreign key in the first table. So all of those kinds of constraints and keys and so forth are consistent. So all the constraints that are known are satisfied. And that's true before a transaction begins, right? We want to make sure that our data always has good integrity. So kind of the default state for the database is that it's in a consistent state. And we want to maintain that consistency. So we can assume that before the transaction, the database is in a consistent state. And the same thing is true after the transaction is over. We're going to perhaps change the state of the database. We're going to add some new content or remove content or update existing content. But when that's complete, the database might be different, but it's still going to be in a consistent state. So all of those kinds of constraints that we talked about are still observed after the transaction is over. The interesting part is kind of within the transaction, right? At that point, sort of all bets are off. In the transaction itself, you might make changes to things that put the database in an inconsistent state temporarily, as long as you sort of do the appropriate thing to resolve those inconsistencies before the transaction is completed. So the transaction boundary not only guarantees an all or nothing behavior for atomicity, but it's also going to guarantee that when the database transaction is over, that the database is back in a consistent state. Third of the ACID properties is called isolation. And this basically is what I was saying before when we think about the database as behaving as if you're the only transaction that's running on the database at any given time. So the isolation idea really has to do with multiple transactions that are in flight simultaneously. Rather than allowing those transactions to kind of interfere with each other, the database is set up in such a way that it isolates the transactions from one another. So multiple transactions are going to yield the same result, even if they're running at the same time, as if they were run sequentially. In other words, one was run to completion and then the other was run to completion in either order. And this applies to more than two transactions. We could have a bunch of transactions in flight all at once, and the database will reach a state that is consistent with all of those transactions executing in some order. Okay, so they don't interfere with each other. The final state of the database is going to reflect all of those transactions completing successfully as if they were run one after the other. So that's isolation. The transactions don't interfere with each other's behavior. And then finally, the fourth part of the ACID properties is durability, and that says that once a transaction commits, its final state is going to be persistent in the database. So at that point, if somebody takes down the database itself or takes down the server, the results are at that point guaranteed to have been written to disk and are persistent, and when the database is next available, those changes will be present. We've been talking about transactions, and one of the things, of course, that transactions do is allow you to either commit or roll back. And I want to just say a few things about the mechanism that allows that kind of behavior to be implemented. So I'm going to start out by asking sort of how does rollback work? When you're in the middle of a transaction and you decide to do a rollback or something bad happens and the database rolls back, how does that actually work under the hood? Well, the database, and this is not necessarily universal, but a fairly common strategy for implementing that, we'll see that the database is going to maintain a log file. So this is kind of a trail, an audit trail of the changes that are made to the database's state. So if you add a row, if you make a change to an existing column, if you create a new table, whatever it happens to be, every time the database's state changes, it's going to keep track of what that change was, and it's going to store that in this thing called the log file. So you could think of this log file as like individual records, and each of those records keeps track of like a timestamp and what the operation was and what the outcome was and so forth, so that you have this path back through time of all of the changes that got made by the database. And this isn't something that's just specific to an individual user or an individual application. This is the database server itself that's keeping this logging information in order to keep track of what's changed in the database. So we know at any given point in time that we have this record of all of the changes that were made. So how does that actually get used in terms of managing transactions within a particular process? So first of all, when a process starts doing a transaction, that transaction is going to get a unique number, so just an identifier, and that allows you to kind of intermix the records from different transactions in the log file. You don't have to create separate files for each individual transaction because you'll have that unique identifier to indicate all of the operations that took place, all the changes that were logged as a result of the behavior of that one transaction. So they're freely intermixed in the log file, and any kind of a change to the database results in writing a log record to that log file that reflects that a certain transaction did a certain action. Now, if the transaction completes successfully, in other words, if the commit statement gets executed, then what's going to happen is any changes that were made as part of that transaction are going to be made persistent in the database. So what I'm saying here, write changes to database. When your transaction is in flight, before you get to a commit or a rollback, the information isn't necessarily, conceptually at least, the information isn't written directly to the files that store the database itself. Those changes might be cached in memory, they might be written to a temporary file, they might actually be stored into a temporary table or something like that. The specific implementation isn't particularly important for this discussion, but when the commit is done, the database management system will write those changes to the database proper, and then it will go and throw away the transaction records from the log file, right? So all of the audit trail of the behavior of that transaction is no longer relevant. It can get rid of those things from the log file because the changes are now persistent and permanent in the database records themselves. On the other hand, if the transaction completes with a rollback, what we're going to do then is go back into that log file and find all of the records associated with that particular transaction, right? We can use that transaction number to look it up. And the information that's in those transaction logs, or the transaction log records, is going to allow us to sort of reconstruct the contents of the database back to the beginning of the transaction. So we can kind of replace the current values that might be stored either in cache and memory or out on the database proper with their old values from when the transaction began. And we can repeat that process back to the beginning of the transaction. So that's how a rollback would work. Again, it's possible, if you think about it, we're using a log file on disk someplace physically, which is itself potentially susceptible to failure. So in a sense, there is never going to be any 100% ironclad guarantee that you will never lose data. If something really terrible happens, somebody spills Coca-Cola into your disk drive, that's going to cause a problem that would just lose all sorts of data. That said, in a production environment, there's usually quite a lot going on in terms of replicating that information, putting it in things like RAID disk arrays that have redundancy built into them, making backups of things off-site, having replicated entire databases, right? So there's a lot of different ways to kind of reduce the possibility or the likelihood that you'll actually lose actual data by doing some of these kind of system administration kinds of things and architecture choices. But the fundamental mechanism still relies on this notion of a log file as distinct from the location on the disks that store the data in order to have this rollback and commit behavior. So we're going to kind of ignore the broader system administration question and just assume that the log file is maintained and has good integrity and can be read and written as necessary. Okay, so how do those log files work? As usual, there's a trade-off here. We have some conflicting goals. We'd like the behavior of the database to be really fast, right? We want to be able to get fast access to disk in order to keep the performance up. On the other hand, we also want to have things be persistent. We want them to be resilient in the face of a system crash. So on the first goal, the notion of being able to do this quickly, it's often the case that we're going to buffer the information that's on its way to disk in memory someplace. That's a very typical way of improving I/O performance. You don't go straight to disk and make your process wait until the disk activity is complete. You write the changes that you want to have made persistent into a buffer, and then at some point the operating system decides that it's time to flush the buffer out to disk and make it permanent. But that might happen a lot later in terms of computer execution time than when you actually make the change to the data. So that increases performance, but if the machine crashes or you lose power or something, then you just have the data stored in those buffers in memory, and the information will just be lost when the system powers off. It won't have made the changes persistently on disk. So we would like to be able to kind of match these two things together, figure out some way to get the best of both worlds so we don't have to wait for all of those records to be written to the log file, but we also don't lose information in the case where we have a system crash. A common approach to dealing with this is the notion of what's called a checkpoint. So if you have taken the operating systems class or poked around in a Unix system much, you'll be aware that there is a system call actually that tells the disk system, hey, go ahead and flush all of the buffers that might be in memory out to disk physically. And that system call is not going to return back to your process until that action has actually taken place, until the operating system can verify that, yeah, there's nothing left in memory that isn't also stored out on disk, so that if the machine crashed at that moment, we wouldn't lose anything. It would all be persistent on the disk. That's the idea of a checkpoint here. Periodically, the database management system will force the operating system to flush those buffers out to disk, making the data persistent. And then it also kind of keeps track of when that checkpoint took place, so that you can kind of roll back to a checkpoint if necessary and add another checkpoint and so forth. But as of the time of that checkpoint, before any other operations are completed by the database management system, you have a consistent record of everything that's taken place in the database as of that moment in time. Now, you're going to then allow the database to continue functioning to do other operations that could potentially be lost if you lost power to memory because you're not sending every one of those log file records to the disk every single time. So this isn't a completely bulletproof way to avoid losing any data. So this is kind of the second issue I've mentioned here. We can't reliably recover from a failure between checkpoints. So if a checkpoint took place and then 2 minutes later the power went off and you lost all of the in-memory buffers, you're potentially going to lose some information because it didn't make it onto disk. So there's a trade-off, right? You're paying for good performance, by opening yourself up to the risk of losing some information. The other issue here, of course, is that the checkpoint itself takes some time and consumes resources. So while the checkpoint is taking place, while the operating system is flushing all those buffers out to disk, you're going to have to deal with some sort of a performance decrease because the database isn't going to be able to do stuff while that checkpoint is happening. So again, it's always a trade-off one way or the other, performance for reliability in this case. But in general, this solution of using checkpoints to periodically flush things out to disk is a good way of balancing those competing goals. To motivate some of the approaches that databases take to managing concurrency, we're going to take a look at some problems that can arise if concurrency isn't handled properly. And this is kind of similar to the notion of anomalies that we talked about in terms of database normalization, right? We saw that there were update anomalies and delete anomalies and so forth. And the investigation of those anomalies gave us some insight into what kind of a system we had to put in place to avoid those anomalies. In that case, it was to do more normalization. But the same sort of idea it obtains here. We're going to talk about some problems that can be encountered if the database isn't doing concurrency properly, and then we'll look at ways that database management systems try to solve those problems. So here's a kind of a laundry list of these things. We're just going to kind of walk down this list one at a time. First of all, what's called a lost update, and I'm again using our dumb little DVD rental database here, but a lost update basically is that you have some datum, some piece of data in the database that's modified by two different users. So here's a scenario from our DVD rental database. So the store, say, has 10 copies of the movie The Incredibles, and we've got Alice and Bob, of course, our store employees. So Alice is in the process of restocking 3 copies of The Incredibles that were returned. She looks in the database and sees that there's 10 copies in stock, and then she's distracted by a customer phone call. Now Bob has 2 copies that he's trying to reshelve or restock, and so he looks in the database and sees that there's 10 in stock and updates that to 12 because we've got these two copies that have come back. Now Alice gets done with her phone call and she goes back and updates the database to say that there are now 13 copies of The Incredibles in stock because she's going to put 3 back in stock. So now we have a situation where we've lost an update, right? Bob's update setting the database to have 12 copies of The Incredibles has been overwritten by Alice's later update by setting it to 13. So the database should show that we have 15 copies of that movie in stock, but it only shows 13. The problem that's really underlying this issue is that the updates have been interleaved. We would like to have in the sense that Alice read, saw 10, Bob read, saw 10, Bob updated to 13, Bob updated to 12, Alice updated to 13, but they happen kind of interleaved with one another. So what we'd like to have is that interleaved updates like this behave as if one of the updates ran to completion and then the other update ran to completion. And we can do that within independent transactions. So the problem is, of course, due to Alice having a hold of old data, right? She first of all went to the database and says, how many copies of Incredibles do you have? Well, 10. And then later on, she uses that old data, which has now been outdated by the fact that Bob did an update to that entry in the database prior to Alice doing it. So we want to be able to prevent that kind of lost update problem. Here's another example. It's called inconsistent analysis. The scenario is like this. Alice is going to do a report on the number of movies on hand, right? So she's going to go to the database and have some kind of report run that tells her how many movies there are on hand. Then, while that report is running, Bob restocks 10 movies and commits those changes. And then Alice's report completes. Now, what Alice is going to see then is that the total number that came back from the database is going to be too small by as many as 10 movies, right? Kind of depending on when the database looked at the table that contained the information that Bob updated during the report running may impact the number of movies that Alice gets in her report. So again, we have this problem where while one activity is taking place, in this case just sort of reading information from the database, it doesn't involve an update on Alice's part, but it does on Bob's part, Alice is going to get different values if these two activities are allowed to complete together. Dirty reads is kind of similar to inconsistent analysis. So the idea here is that you're using data that has been rolled back by another user. So here's the scenario. Alice starts her report again of the number of movies on hand. Bob then restocks his 10 movies, but doesn't commit those changes to the database. Then Alice's report finishes. Now, she's going to potentially have issues with that report, but then turns out Bob was restocking the wrong movies, and he decides to roll back that update. So now Alice's total in terms of the number of movies could be too large by up to 10 movies, depending on the timing of these specific database accesses. So it's called a dirty read because Alice's information is based on data that's no longer clean, right? She saw this temporary change to the number of movies that Bob made and then reported on that basis, and then Bob reduced the number of movies, so the total that Alice is going to see could potentially be too large. Another similar thing is the idea of non-repeatable reads. So we would like, when we read a value out of the database and then go back later and read the same value, to get the same value on both reads. A non-repeatable read is a situation where we don't have that consistency. So we're going to read a piece of data more than once and get different values. For example, Alice runs an inventory report that's sorted by film title, right? Here's all the films by title, here's some that are in stock, and so forth. Bob sees that although there's 10 copies of Incredibles on the shelf, the database shows 0. So something is wrong with the count in the database. So Bob goes ahead and updates the database to reflect the actual number of copies of that movie in stock. Now Alice runs an inventory report sorted by release date. Now you would expect that the information that she gets from the database would be the same whether she's sorting things by film title or by release date, right? But what she's going to see, even if she tries to do these two things in the same operation, the fact that Bob will have made a change to the number of copies of Incredibles is going to result in the second report reflecting a different number for that particular film. So Alice ran 2 inventory reports on all the movies, but one of them shows up to 10 more movies. So she's reading the same things twice in a little bit different way, presenting the data in a little different way, but the two different versions of the data don't match up as she expects they should. Then finally, phantom reads is similar to a non-repeatable read, but instead of a change to an existing row, it has to do with new rows that are being added. So Alice is going to do the same thing, run her inventory report sorted by title, and then sorted by return date, by release date. And in between there, Bob is going to get 5 copies each of 5 new releases. So he's going to basically be adding new DVD titles to the database, and then Alice sees her second report. So although Alice ran these 2 inventory reports on all the movies, the second report is going to potentially show 25 new movies, 5 copies of each of those 5 new releases. again, she would expect to have those two reads of the database give her back the same values. Something to keep in mind about these concurrency problem examples that I've just outlined is that those are situations that could obtain if the database wasn't using transactions or had transactions implemented improperly. In fact, with transactions in place, we should be able to avoid all of those concurrency issues. The consistency issues, the phantom reads, all those things that we just talked about should be solvable if we have transactions available to us. So question comes up, well, okay, so let's assume that we put these things in transactions. How do those things actually get implemented? What's the mechanism under the hood that the database is going to use to provide that capability? So we're going to look at one particular approach to solving this issue, and that's called locking. The idea here is that we want to prevent multiple users from changing the same data inside of a transaction in a way that allows that change to be visible to other transactions. In other words, situations where we might violate that principle of isolation. Isolation says two different transactions should behave as if they're the only transactions that are running, and the result of completing all those transactions should be something that leaves the database in a consistent state that would have been similar to having had all of those transactions just execute one after the other in sequence. So this is one approach to doing that. So we want to prevent simultaneous access to the same data when we have multiple transactions in flight. And locking is a common and time-honored solution to this problem. So essentially what we're saying when we talk about a lock is we're going to give access to one transaction to some portion of the database. Now, a simple-minded way of locking this, or doing locking, would be to just say, well, only one transaction at a time can access the whole database. That's going to solve the problem in sort of a trivial way, right? Because no two transactions can ever be active at the same time. However, it's also going to mean that performance is going to be terrible. So, in fact, the way that locking is usually employed is to do the locking on a finer grained level, where you're going to lock maybe a table, maybe a row within a table, maybe a column within a row. So there's various levels of granularity that locking can use, but whatever that level of granularity is, it's going to solve the problem. So the granularity has to do with the portion of the database that's locked. And we're going to look at three different types of locks that could really be employed in any level of granularity. Often it's a table lock or a row lock. Okay, so of those three, exclusive, shared, and two-phase locks, let's talk about exclusive locks. So an exclusive lock basically says nobody else but the transaction that holds that lock can do anything with the resources that have been locked. Let's just assume, say, a table lock. So the particular transaction that holds the exclusive lock is the only transaction that has access to a specific table. Everybody else has got to wait for the lock to be released in order for them to access the table. So if there's only one transaction that wants to access a given table at a given time, it's going to get the lock and nobody else is going to be any the wiser. On the other hand, if that table is especially popular with a bunch of different transactions, one transaction is going to get the lock. The others are just going to be queued up behind that first one until it's done or until the transaction completes. It's going to release that lock, and then the next transaction in the queue is going to have access to that table. So that's an exclusive lock. One of the problems with an exclusive locking is that of deadlock. So, for example, in a really simple case, we have two transactions that are accessing two different tables. So, in the case of a table level lock. So transaction A, the first transaction, is holding a lock that transaction B is waiting for. And similarly, transaction B is holding a lock that transaction A is waiting for. So those two transactions now are waiting on one another, and they aren't going to ever make progress toward completing the transaction because neither can move forward until the other one does, and therefore they're in this state known as a deadlock. Now there's some ways to deal with this. One of them is called the detect and break strategy. So for example, what we'll do is choose a transaction, and I've put it at random here in quotes. Oftentimes the one that's chosen here is the one that was executed most recently, sort of a first come, first serve model. You're going to just choose a transaction arbitrarily and cause it to roll back. and that's going to allow the other transaction to complete, right? So in this simple case where we just have two transactions that are deadlocked, if transaction A got started first and transaction B got started after that, transaction B would be the one that we would cause to roll back. And because B was holding a resource needed by A, now A can continue forward and eventually complete, releasing its lock that transaction B was waiting for. Now, the cool thing about having done this in the transaction context is this doesn't necessarily result in the application that's running transaction B in this example from receiving any kind of error messages, right? All we're saying is transaction B is going to temporarily roll back so that transaction A can complete. And when that's done, the database can itself restart transaction B and allow it to run to completion. So this behavior, this locking and even the deadlock detection can be done in a way that's transparent to the application that's using the database. Another approach, so this is kind of the detect and break approach kind of makes the assumption that in general, let's assume that everybody's going to play nice and nobody's going to lock things being locked by them. The other approach that's common in this exclusive write lock case is what's called pre-declaring your lock. So instead of waiting until a deadlock occurs and has to be detected by the database management system, instead what we'll do is each transaction will try to acquire all the locks that it's going to need prior to starting the work that the transaction is wrapping up. So that particular transaction will eventually get access to all of its resources, all the tables if we're doing a table level locking, and only then will it execute the database commands that are inside the transaction. Because it's already got all the locks it's going to need, it's guaranteed to be able to finish without ever deadlocking with anybody else, and then it will release all those locks at the end, and then another transaction would be able to acquire those as part of its process of teeing up the locks that it needs to do its transaction. One of the problems with exclusive locks is that they are just that. They're exclusive. So when we talk about, say, an exclusive table lock, we're saying only one transaction has access to that particular table at any given time, whether it's reading from it or writing to it. A shared lock, also called a read lock, is a slightly less burdensome approach to doing this. So a shared lock will allow for simultaneous reads, but not simultaneous writes. Okay? Exclusive locks prevent both read and write from any other transaction, whereas a shared lock only says that about writing. So if a particular transaction is only going to read from a table, it's only doing select statements on that table, the R of the CRUD pattern, it could get a shared lock on that table and go ahead and start reading. If there was another transaction in flight that also needed to have access to that same table and it was only going to read from it, it could also be granted a shared or read lock on that same table. And that could be the case for as many transactions as necessary. As long as we're not making changes to that table, we can read from it from as many transactions as we want. It's only when we have to make a change to it that we need to have an exclusive lock, or a write lock, it's sometimes called. So the fact that we can open up shared read locks on a particular table is a way that we can keep track of whether when a transaction needs to have write access to that table, it can check to see, hey, are there any shared locks on that table from other transactions? If so, we can wait to have all those shared locks released by other transactions before granting an exclusive or a write lock to the transaction that needs to make a change to it. So we can improve the ability of multiple transactions to get information out of the database if they're just reading, and not have to have everybody stop and wait no matter what if we were just exclusively using exclusive locks. So all of the shared locks have to be released before the exclusive lock is granted, but it'd be entirely fine if we had some shared locks active and somebody asked for a shared lock on the same table. Another approach to doing this that kind of mixes these two a little bit is what's called a two-phase lock. The idea is that we're going to have shared locks that can be upgraded to exclusive locks if there needs to be some sort of a write done on a particular table. So this tends to increase concurrency, as does just the use of shared locks in general, and it kind of minimizes the amount of data that needs to be locked, and it also minimizes the amount of time that the data is locked. So we can kind of move from a shared lock to an exclusive lock and back again as necessary. And we can still employ the rollback mechanism if other transactions are holding locks on the same data. So the detection things that we were talking about previously. Now, one other approach to doing concurrency that doesn't involve locking is called multi-version concurrency control. And I'm mentioning this because this is the concurrency mechanism that's used by Postgres, which is what we've been using for our examples. And this is just some information kind of gleaned from the Postgres documentation. Essentially, rather than having locking and keeping things out of the database at different places, what MVCC does is treats the SQL statement or the transaction as having access to a snapshot of the data in the database as it was at some point kind of in recent history, right? The documentation just says some time ago, but fairly recently. So when that statement starts, you're going to basically show it a view of the database, and I don't mean a SQL view or whatever, but just sort of conceptually, a view of the database as of some point in time in the past. And that will be the view that SQL statement has of the database. So some of the things that does is it prevents the different statements from seeing an inconsistent view of the data, right? So within a given transaction, you're going to have that particular snapshot of data available to you for the duration of the transaction. So if another transaction starts a little bit later, they might get a different view of the data. The positive side of this is that it minimizes contention, right? So if everybody has their own different view of the data, they're not going to find themselves in these kinds of contentious locking conditions. So the MVC also does this in a way that allows reading and writing to basically not conflict with each other. So we don't have this issue of the two-phase locking thing or promoting an exclusive or shared lock to an exclusive lock and so forth. So writing is never going to block reading, and reading is never going to block writing. Now, obviously, there's going to be some more complex underlying issues here in the sense of we're pushing this all off kind of onto this notion of a snapshot of the data as it was at some point in the past. The database is going to have to figure out as transactions end, they're going to have made some changes to the state of the database as of some particular point in time, right? They're going to make changes and commit those changes. The guarantee that transactions make, consistent with the ACID properties that we talked about, is that the result of multiple transactions that were in flight simultaneously is going to be as if all of those transactions completed in some sequential order, right? So if we got transaction A and B and C that are all running simultaneously, the result that's going to end up in the database, to be consistent with the ACID properties, is that there's going to be some ordering of those transactions that would result in the final state of the database if they are executed serially in some order. So it might appear that the final state of the database is consistent with a scenario in which A ran to completion and then B and then C. But it also might be that the database would be in a state that's consistent with the sequence A, then C, then B, or any other permutation of these three transactions. Now, with that in mind, let's go back and take a look at some of these concurrency problems and how they could be solved by using transactions and locking or transactions in MVCC. So first, the lost update problem. Remember, this was where Alice had tried to say that there were 3 more movies in stock, and Bob tried to do 2 more movies, and we got the wrong totals. What we'd want to do in this case is to create a transaction for Alice's updates that would include step 2 and step 4, and a transaction for Bob's updates that would include step 3 and step 5. Right? So there's a transaction there, and there's a transaction here. And again, the behavior that we're trying to come up with is to put the database in a state that would be consistent with these transactions executing serially in some order. So you can see here that the way I've drawn these lines sloppily, that these transactions sort of interact with each other in some sense. What's going to happen is that the database is going to behave as if these things were going to be serialized. So it could complete these two transactions in one of two ways. First of all, if it allows Alice's transaction to go forward first, what would happen is Alice would start this update operation. She would see 10 movies or 10 copies of The Incredibles in the database at that point, and then she could go get distracted by her phone call, and the transaction is still live. Now at that point, Bob might want to get in here and try to make a similar update, but his transaction is going to be locked out of reading information from the table that Alice has already locked until she comes back and updates her 10 to 13 and completes the transaction, at which point Bob's transaction will be allowed to proceed to read this information out of the database, and instead of seeing 10 movies in stock, he's going to now see 13, right? Because Alice's transaction has already been committed. He's going to then update that to 15, and his change to the table will also be reflected in the final state of the database. So if this is time going forward here, by the time we get to here, both of those transactions have completed, and we will no longer have a lost update. Now, it'd be entirely possible for the transactions to be executed in the opposite order. The way I've written this scenario here, it sure seems like Bob is getting started after Alice started to do her thing, but it wouldn't necessarily have to be the case, right? Bob's transaction might get in first. He's going to see 10 movies in stock. If Alice jumps on and tries to check the number of copies of The Incredibles available, she'll be locked out of that until Bob is done making a change to update it to 12 in his case. And now Alice, when her transaction kicks off, is going to see 12 movies in stock. She'll add her 3, and the final total again will be 15. So no matter which order those two transactions complete in, we'll end up without the lost update problem.